Skin has become shiny. It's now entered reflective.
Okay. Guys. Oh, I didn't wear my thingamajig today. Hello. Hello. Okay. Let's go over first of all Newton's laws. This is a reference to forces. Okay. Well, before we start, just a reminder of what a net force is. So this refers to net force. Also called or known as an unbalanced force. It has units of newtons, like all forces do. All forces have a unit or use the unit of newtons. You can measure it with a spring scale. How many newtons? It is a vector. Any force is a vector. It has a direction positive to the right, negative to the left, negative if it's acting down or south. Now, here's a free body diagram. Let's say you are, let me draw the situation and then the free body diagram. So this is some sort of wooden block, mass M. It's on the ground. Being pulled. There's some force parallel, horizontal to the ground. Call it an applied force. There is friction. In the opposite direction. The object, this block is moving this way. It's accelerating that way. It's open, should be open. Oh, thank you. Susan. And that force is when there's one force greater than another. Another way of saying is that the overall forces are not balanced. They're unbalanced. This FA here, the way I drew the arrow, is longer than the force of friction. F of A means or stands for applied force. Okay. And F of F stands for force of friction. Different ways of writing these. You may be used to something else, but we're going to use these notations. Okay, so you can see just the way I drew it. FA is bigger, FA is greater in magnitude. Okay, they're not balanced. One is bigger than the other. If they were equal, they'd be balanced. I know this is not a free body diagram. Should I draw it? I don't need to make the point. The net force does not equal 0. There is a net force. It does not equal 0. Because FA is bigger than F of F. What is the net force? The net force is whatever's left over of the applied force after you subtract friction. So there is some net force. Some numbers here. I'm just making this up. Let's say this is 100. Let's say this is 10. Your overall net force would be 90. Yes, I'm not worried about direction. There is a direction, it's to the right, but I just wanted to give you a number other than 0. There's a net force. You need to know what that, or be reminded of what that is. Okay, so here are the Newtons. Here are Newton's 3 laws. First one. No. I jump right to the third one. Mine's on something else. An object moves with constant velocity. If it's already moving, it continues to move at constant velocity. Or stay at rest. It could be at rest. And here's one of the keys here. Unless what? Unless a net force, that's why I referred to it at the beginning. Unless a net force, I'll just put F net, is acting on it. That's the first law. So really, we don't see a lot of it here on Earth because there's friction, there's air resistance. But if you were in space and you just were to tap on, let's say you threw a ball in space, it would keep moving in a straight line, unhindered. And if it was far enough away from the Earth, it would just keep moving in a straight line. So what is constant velocity? Constant velocity means constant speed. So if you were able to throw it at 2 meters per second, it would keep moving at 2 meters per second. And same direction, constant direction. Doesn't change its direction, doesn't change its speed. Right? You can approximate that on an air hockey table. If you ever play or have played air hockey, you can hit the air puck or the puck and it'll keep going. There's very little resistance. It'll slow down eventually, but for the most part, it'll keep moving with a constant velocity, at least in the short term. Two, that's the first law. An object moves with a constant velocity or stays at rest, stays at rest unless a net force acts on it. Second law essentially is this. It's just this, and I'll go into more detail. We already described F net. It is a vector in the same direction as the acceleration. Okay. So this is, let's see, this is west. I want to make it a different color. This is west. The acceleration will be west. Usually we put directions in brackets. Always the same direction. All right. A is the acceleration or deceleration. We usually use the generic word acceleration to mean either. It is a vector. I just mentioned it's in the same direction as net force. It has units of meters per second squared. What is acceleration? Just a brief reminder. It's how quickly something speeds up. How quickly does it reach a certain speed? That's your acceleration. Or slows down. Your mass has units of kilograms. And it's the same everywhere. The mass is the amount of matter. Same on any planet, same on any moon. It's the same sun, same value everywhere. In kilograms. It's not, when you use kilograms on a daily basis, you refer to it as weight. The proper term for a measurement of kilograms is mass in science. Weight is something a little bit different. Weight, we'll get into next, the next section. It can change. This mass cannot change. It's the same value everywhere. Whatever that particular mass is, it's the same everywhere. The weight of an object can change, can vary. Mass can't. Okay, so it's an easy equation to work with. It on the surface, it can get more difficult because we need to find the net force. what we're interested in is finding the net force, find that to find the acceleration or vice versa. Given the acceleration, find the net force. And this part can be difficult. What describes the net force? That's why we need free body diagrams. Just an easy rearrangement. Why don't you, don't tell me, why don't you do that now? Rearrange it from mass and acceleration. It's easy. You need to know how to do it. Okay, so doesn't matter which side you put it on. F net over A is mass. That's a scalar, remember? That's why I don't put a little arrow on top of it. Mass is a scalar. It's not a vector. You can't represent mass in terms of arrows. You can represent force or acceleration in terms of arrows because it's a vector. And we use this probably the most, F net over M. Okay, third law. For every action, there's an opposite and equal reaction. Okay, I mean, the very simple example is just putting an object, like we talked about, placing a block on the floor. The floor is going to feel a force because the object's leaning against it, pressing against it. So the floor feels a force down equal to the weight of the object. And the object will feel a force up from the floor, by the floor. We call that the normal force. That's why I drew these arrows equal. Now I'm just going to write it in terms of magnitude, not direction. The directions are opposite. You want to write, I won't confuse you. I'm just writing them. When I skip the arrows on top, that just means absolute value. They're equal in absolute value. Opposite in direction, as you can see in the diagram. Okay. You push against the wall. It's the wall. You push against the wall with an applied force. That wall is going to react back until a point where it can't anymore, until the applied force is too great. The wall will, it'll flex. You don't see it, the normal force, because it's perpendicular to the surface, a reactionary force. You don't see the flex, but even a wall will flex slightly, like an elastic band, and push back against you leaning on it. Rocket ship. inside the rocket ship chamber. This is all steel here. The rocket, this part of the rocket here, this part of the engine, it's all encased. This part will push against, there's gases being created. There's gas being created here when you burn the fuel. So this inner casing, this surface will push down with a normal force, and the gas will push up with a greater force. Well, I mean, at the beginning, it's equal, right? So at the beginning, there's an opposite and equal force. It's not really, anyways, that's a little confusing. At the very beginning, it's not moving anywhere. They're equal forces. Anytime you push against the surface, you're getting a react. Just pushing, my little finger pushing against this table here. Fact that it's not moving through it means there's an equal opposite force pushing back against it. If there weren't, my finger would go right through the surface. Okay, so I've got a little handout for you. This handout actually deals with treating forces like vectors, drawing little arrows. So I want you to try this out. Try up to number 4. 4 is a little on the difficult side, but I'll go through these with you, but give these a try first and see what you can recall from our previous section on adding vectors. Adding vectors. The force is a vector. See the first page. Let's try. Page 95, 1 to 4. 95, 1 to 4.
Nothing else? Is that it? Five you can use. That it? Plus y, the other thing you can take the
Use arrows first. Show the arrows how you would add them tip to tail, how you find the resultant, draw it with a different color, and then do the math. Okay, what do I need to do? Just gonna copy something, guys. Give me a minute while you're still working on that. So.
Yeah, but then like, how do you like find like basically what half of this? Like basically, it's like the actual like proper like net force like somewhere in between here. Sector and square, yeah, you see those a lot. That's because I fell asleep yesterday. I don't remember that part. I get it now. Yeah, yesterday we went fountain. We did. No, like the vectors. Because I just did this, whereas I probably should have done this. Yeah. No, we don't do replaces your gum. So then you're actually Right. So it would look like this. Half theta equals that, so that's theta. Who's two? Huh? That's two. That's two, and then that's two. Oh no, because like I'm using these two, like Pythagorean theorem, so I want the whole thing. How would you do, how to design? But then I haven't found my problems yet. Yeah, because I was able to find it because I have this.
And then you send us through.
Yeah.
The other way.
Sorry, have the. Have all the silver.
This I like the middle.
Oh, yeah. It's really great. So I just met
So it's
4.9.
4.9 Newton.
This, I told her to hole punch it. Is there a hole punch here?
Oh.
Just be patient. We'll go over the questions in a second. Okay, you can try. We haven't gone over all the details yet, but you can, I'm sure you remember all this. Page 99. Try those questions as well. While I'm just getting ready for you here. Next page is the other side. Yeah.
Page 99, right?
Yeah.
All the way.
Yeah, they should be pretty easy. Yeah, give those a try. I'll go over page 98 in a second here.
Wait, does net force have like, net force is vector, right? Yeah. Yeah, so it doesn't matter. I think those right. Actually, it's been a long.
I'm sorry. I put meters per second squared for mass.
Oh, yeah. Acceleration equals, 0.11 meters per second south.
Acceleration.
I think it does. Acceleration is a vector. Or acceleration is a vector. This is right, but you make rubber shine.
Yeah.
95, okay. So 95, let's go with 95. Let's go over page 95. Number 1. I'll draw the arrows first, add them together tip to tail, and then do the math. So we have a force. It doesn't matter whether it's a force, displacement. We treat them the same way. We use arrows to represent the magnitude. The length of the arrow represents the magnitude. And the direction of the arrow represents the direction of the force, the vector. They're both to the east, and they add up tip to tail, just like I showed you here. And they add to give what's called a resultant. In general, the term for what they add up to is called the resultants. In the case of force, it has a particular name. It's called the net force. So the net force is a resultant. When you add up the arrows. And now these vectors are parallel, so we can simply use addition or subtraction if they're parallel. In this case, they're in the same direction, so we just add them. The magnitude of the net force is just 2 plus 3, which I think is still equal to 5. I don't know. Maybe they might change it. F net. Kidding. Direction is important as well. You can see just the direction of the red arrow here. The resultant is east. 2. Read over number 2. So there's a force that's 2 newtons east and one that is 3 newtons west. I didn't draw them. I separated them one on top of each other, but they should be drawn one on top of each other. That gets a little sloppy. It's 3 newtons west. The resultant is drawn from the tip of the first vector, which is here. The tip of the net force will match the tip of the first vector. Not the tip, the tail, pardon me. Tail to tail. The tip of the net force will match up with the tip of the second vector, the last vector. And you just fill it out in between. That's your F net. I mean, I'm just going to work with magnitude. 3 minus 2 is 1. But it is to the left. So it is, you can put it, you can add a negative after the fact, or you can just put west, either one. Negative or west. You could write 2 minus 3. You can do it that way as well. I just tend to work with magnitudes. Yes. Say it again. East is going to be positive. Yeah, I mean, you could put that on top of it. Either, that's fine, either one. Okay, read over number 3. East, we have one vector that's east. Just going to drop the units. I'll add them back later. And a force that's 3 south. They're going to add tip to tail. They are perpendicular because east is perpendicular to south. And the resultant is drawn from the tail of the first so that the tail matches, tail of the resultant matches the tail of the first vector to the tip of the last. So the tip of the net force will match the tip of the second vector. Different math because it's no longer parallel forces. We need to know what this angle is. So the net force squared, I'm just working with magnitudes. Yep.
You have to do, the force have to be negative even if we.
No, either one. It was just a, you can, I mean, I like, for clarity's sake, just do that. That's fine. Or you can just put -1.
But can we put positive?
If you left like that, as long as it's clear to me, you know what you're doing, right? That's clear to me.
Which one is approved by?
Either one, yeah. You can put negative or -1. Always check with your teacher, but or that. Or newtons. Don't forget the unit at the end. I'm not done. I have to include the angle as well. I would use the opposite over adjacent. 56 degrees. Go back to it. Notice it's leaning to the south, right? Leaning down to the south. The other vector that makes up the angle is this purple vector here, the 2 vector. That's pointed towards the east. So it's south of east. Read over 4. 4 is a little more difficult. I'll draw it out for you. Okay, so 4, we have a 2 Newton vector east. And then we have a 3 Newton vector, 3 Newton vector north of east. Okay, the resultant is drawn from the tail of the first to the tip of the last. That's my F net. So what am I interested in? I'm going to redraw this. I wonder if I can, don't laugh at me. I'm learning new stuff with this thing. No, I want to lasso it, whatever. Ah. Can I do that? Oh. That's so cool. Sorry, I know to you, you're laughing at me, but I like that. Okay, that's my F net. What am I after with my F net? I am after, make this a different color like green. I'm after this component. It's what I want to find. My F net X is parallel to the X. And my F net Y parallel to the Y. And my angle in here. Okay. So let's go back to the diagram on top. On top, I'll just redraw this. And this second vector has a component. An X component. And it has a Y component. Okay, what is F net Y equal to? F net Y is just equal to what I called Y above. It's the same thing. What is F net X equal to? It's just equal to 2 plus what I called the X component above. So let's figure out these components. These components are F2, the X component is 3 times the cosine. I'm just going to give you the value. You can figure it out. You now know how to do it. 2.7 newtons. Y component is the sine of 3, which is 1.3. So this net Y component is 1.3. And this X component is 2 plus 2.7, or 4.7. Those are my components, my X and Y. I'll just redraw it again. What? Okay. So this is 4.7. And this is 1.3. So net force squared is equal to 4.7 squared plus 1.3 squared. Net force works out to be a little bit bigger than 4.7, 4.9 newtons. And the angle, because I need, remember, force is a vector. You're talking about a force at an angle, you need to give that angle. If it's simply parallel to the x-axis, you just write east or west. Opposite over adjacent. Repeat, 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 but that's good. You can see how this is applicable in so many areas. So the angle works out to be 15 degrees north of east. Okay, next page, 99. How many people have finished that page? Okay, so most people. Okay, for those who haven't, we'll come back to it in a second here. Net force is used. Remember, one of the key points, remember acceleration and net force. It's supposed to be an and. Are in the same direction. Remember, with acceleration, you have to mention the direction as well, unless they ask you for the magnitude. The question is, what's the magnitude? Just give the positive value. Acceleration. Those should be straightforward. We'll come back to it. We'll do it on the board. What's the weight? Let's go on to weight. See if you remember. So little notes on weight. Do that page, and then we'll come back and we'll do them all on the board. Okay. Weight. It's not what you call, not measuring what you call kilograms. That's the measurement for mass. Weight is the force due to gravity. It's the same thing. And we label it Fg. Okay, yes, it's a vector. Usually we just calculate the magnitude, though, of the weight. And you know from last year how heavy something is when we're talking about physics and how heavy something is depends on not only the mass, but where you are. Depends on the pull of gravity. On the surface of the Earth, gravity acts at 9.81. On the moon, it's far less. So the weight of an object on the moon is less. That's why if you ever watch videos of the lunar landing, yes, it was real. I don't care what people are saying. You see the astronauts moving, when they take a jump, they move fairly slowly compared to what we'd see on the Earth. That's because the weight of the astronaut is less. So I'm just writing down the magnitude. Okay, we know it's always downwards. Always, Fg always acts downwards towards the center of the Earth. Okay, Fg is equal to, this is the magnitude, I didn't put an arrow on top, is equal to m, the mass, times gravity. Whatever the gravitational acceleration due to gravity is. G is acceleration due to gravity on whatever planet. On the Earth, it's 9.1. Okay, it's also known, and it's in meters per second squared. It's also known by a different quantity. It's the same thing though, same value. It's also known as the gravitational field strength, calculated in the same way. We use, when we refer to it as gravitational field strength, we use a different unit. It's equivalent. 1 meter per second squared is equal to 1 Newton per kilogram. Where does that come from? It comes from acceleration is equal to force over mass. That's where it comes from. That's how we know they're equivalent units. This value can change. That's the changeable factor. This value cannot. That's whatever the object is, the mass is the same everywhere in the universe. Mass doesn't change. It's just a measurement of the amount of matter. As long as you're dealing with the same object, you're dealing with about the same amount of matter. So mass doesn't change. G can change depending on where you are. Above the surface, at the surface, different planet. It's, for us, equal to 9.81 on the surface of the Earth. I'm just using magnitudes. I know it's negative. I'm just calculating magnitudes. Yeah. Yeah.
This means that, I don't think, if meters per second squared equals newtons per kilogram,
Yeah.
then the second squared equals.
No, it doesn't follow. Yeah. I mean, I could go into detail for you, but no. Meters does not equal newtons, right? So second squared can't equal kilograms. It does work out, but we can look at that later. Yeah.
So when we're like writing acceleration specifically in the context of like gravity, we should always use the newtons over kilograms.
If the question is what is, let's say you get a question, what is a gravitational field strength? Then you use newtons per kilogram. Use it in the context of what is that it's asking. Yeah. Yeah.
For the practice exercises, go over question 5 on page 95.
Number 5 on page.
95. That's the first page, question 5.
Yeah, you didn't have to do that. I think I just said 4, right? I could go over later. Yeah. Yeah, I wanted to stray away from that for now, but I can go over it after I finish this. Let the others work on stuff, and then I can. Yeah. Now, so it's simple. Weight is just this. Take the mass, multiply by G, which is 9.81 on the Earth. If it's a different planet, then you will either be asked to calculate it. So typically you get a question like this. Take a look. Let's take a look at page 103. You look at page 103, number 3, it says, what is the acceleration due to gravity on the moon? They give you the weight. That's the weight. Okay? This is what you're being asked to solve for. They give you the mass. It's in kilograms. Mass is always in kilograms. Just rearrange. This G, this is a subscript. That's just telling you what type of force it is. This is an actual number. They're two different things. Don't get confused. I mean, they're related, but the G on the right is a number. It's a constant, 9.81 on the Earth. On the moon, you're gonna calculate it. It's gonna be less. G is less on the moon. You'll figure out, should be approximately, divide the Earth's value by 6. That's what you should get. G is on the moon. Okay. So page 103, simple questions as well. If you haven't finished 1 or 99, do that. Finish that. Then you can work on 103. We'll put 99 and 103 on the board in a second here. Jake, you had a question on 5, right?
Yeah.
Just come here. So otherwise they're going to get, I don't want to divert their attention.
Excuse me, I have a worksheet, please.
Is it this one? Yes, you were out.
Yes.
You're welcome. We did page 95, 99. We're working on 103. 95, we only did up to 4. I just went over 95, so that'll be in the video when I post it. Yeah.
I think I got it correct, but I'm not sure. So I did this triangle right here.
Yeah,
and I
good.
did this triangle right here. So
Yeah.
I took all the equations. So I got 2 newtons, 1, 1, 2, 3, 1, 5, 8.
Did you add, now these two components that's greater than that, right?
Yes,
So did you subtract that from that?
I did, and
Good.
I got that it is 1.39 newtons.
Sounds good.
And then I totaled up the
Perfect.
west, and then I got this. Like,
Now, did you use Pythagorean theorem to find that?
Yeah.
I think you're right, yeah.
okay.
Yeah. Everybody's right. Yeah, 3.3. Yeah, perfect. And then it's how many degrees? 25 degrees south of west.
Degrees. Shoot. Wait. How do you?
I just draw the components out. So you got, let's just see again. So we're clear. I would just draw those components. You got this as a westerly, so you draw that out to the west, and then that one as a south, draw that out south. And then you're trying to, I mean,
Wait, you just subtract the degree, right?
can I draw it here?
It's 61 minus 38 to find the degree, right?
Well, just watch. Let me draw that. You need a diagram. That's the 3.3 vector, 3.03 vector. And that's the 1.39 vector. And here's your resultant.
That's the resultant.
That's your angle there. So opposite over adjacent. So 1.39 over 3.03.
So if I took this, and this was 38, and then I would subtract 61 from 38.
Yeah, you did that right.
That.
That
So
way,
that-
what-
So
Oh, no, don't
get
find
the-
your angle that way. Do it this way.
right. Oh, okay, fine.
Yeah.
Gotcha.
I just have a question. So do you send the textbooks with students at home or it just stays in class?
Some of them stay in class because sometimes we don't. Yeah, sometimes.
So it goes sometimes.
Sometimes. Yeah.
Okay.
Are they asking or?
Yeah.
I mean, it's heavy, right? Take a look at it. I don't assign everything out of it. I do assign some stuff out of it. So, yeah. That's why I try to lock the door or close it. Yeah. Okay, we'll start putting up page 96. Should be straightforward. Just trying to think here. It's 11:30. Will I give you? Yep.
For number 4, I got the same answer as you, but I used the cosine and sine one.
Perfect. Yeah, that's a different. I don't teach that, but perfect. You know what? It's simpler, right?
Yeah.
Yeah. Is anyone, has anyone leaving their textbook here? Okay. These,
What if like I write the gravity as like meters per second squared with?
yeah, that's the way we write it in general. Unless you're asked the question, what's the gravitational field?
But if I write that as like meters per second squared, we can like mark it.
No. No.
Okay.
Let me just take a look. This is the formula sheet that I need. Yeah, I think I'm gonna copy, I was gonna copy it for you, I think I'll do that now.
This is my own.
Yeah, can you erase that there? Thanks. I'll do that, thank you, that's perfect.
Mr. Glover,
Yeah.
for gravity,
Mhm.
let's say like the first question is 25 kilograms. So can we multiply that by 3 times 24 or 9?
Let me look a look. That's the, are you talking about page 103, number 1?
Yeah, do we get a negative result or a positive result?
Weight, what is the weight? I'm more interested in magnitude for this page, just so you know, but in general, weight is downwards, just put downwards, or negative, so. But focus more on the magnitude unless otherwise asked. So, yeah, weight, you can put negative or downwards. Give me a second, I finally got a formula sheet for you, so I'm gonna copy that. Then I can, start putting the answers, some of those up on the board for you. We'll do that now. Okay. You guys are gonna do my page 1 to 6. Oh, you just wrote answers. I know they're easy.
That's like, what is the line?
I wrote mine.
You're the man. Okay, just write the full equation.
Yeah, I can do that. That was very long.
That's too late. I got nothing. Okay. Let's see here. Let me check. Just round it to 6. Two, 25. Show the calculation, how you did, right? Write the formulas at the beginning of each, and then show the substitute. They're all right, so as far as, say anything about, include the direction, so the forward, that's south, right? It's a magnitude, that's fine. Acceleration of from east, that's east. Oh, south, you did put south, perfect. East there. That's a magnitude, that's fine. So just a magnitude, that's great. It's acceleration of, it's east, put east there. So just those two, east and east. And put those on the board.
All of them?
Yeah, put them on the left side. I'll be back in a second.
First one's east.
East. Assert my superiority.
No, I can't write on the board with my tiny writing.
Assert my superiority, Franco. Is that a brown one? Is that brown ones?
They're brown markers.
Yeah, they're brown markers. I don't know. That's the last bit. Okay, 100. Not yet. I don't think so. Hey, Franco, do we have to do 100 this one?
I don't think so.
I don't think so.
It's 105.
Whether you do it. Wait, so, fine. Page 99. You have to do 99 and 103?
No, I think it
Okay. Number 1.
F net equals MA.
Force equals mass times acceleration.
Your force so small. That force actually.
Mass times acceleration. Okay, just know that. And then
So 9 equals 20 times A.
9.0 equals 20 times A.
Now, I know for
A equals
9 over 20.
9 divided by 20. 20.
That equals 0.45.
Acceleration equals 0.45 meters per second squared east.
No, right, that entire thing. They think it means enter.
15.0 equal n times 8. Mass equals 15 divided by 8. Damn, that hit me so hard. It's a revelation. Mass equals 1.8 what?
Yeah, basically 103.
Can you do it? It'll be highly appreciated. Wait, which one? Wait, 103. You can try solving that.
Which one?
Any one of them. Anyone.
They're-
Yeah, we've already done them. Which one do you want?
No, I'm saying if you
Oh,
put that on
board.
board.
Oh, okay.
All right, I'll
Any specific one?
No, I think maybe start from question 3.
Start from question 3.
I got this. No, wait, yeah.
Yeah, can you go over there?
Wow, I'm sure.
Go over there, Frank. Go, you go.
Where was it?
Think of this one step first. Tissue result. What direction is the result factor?
Oh, you're helping him?
Oh,
Oh, I didn't check your page 103 though. I mean, I can do that. Are you gonna write the full formula for me? You're a good boy then. Take back what I said. I like Keeners, that's good. Yeah, just write like the full formula. It's just for the sake of them seeing it. Show all calculations, ladies, gents, always good. When they say, yeah, make sure you include with number 1 down, right? Number 1, it does say weight, so I'll include down, yeah. 4, show the calculation. You got them all right, good job. Just show the formula, guys, always show. Listen, for clarity's sake, because you guys may be used to doing it differently, when I'm marking a test, I want to see the formula, I want to see the substitution, then I want to see a final answer with unit and direction. And, pardon? If there's a, yeah, if there's a. Okay, I've got formula sheets for you. Thank Franco. I have one as well. This actually looks a little better, so I'll do that. Well, I will attach this on the test that you have, so you'll have the same one. So they're putting up the answers to page 99 and 103, just check your answers. Check about the two there.
Unit. No, unit.
Listen to music?
Or M.
We can, okay.
Wait,
Or wait.
Yeah, does it help you focus? Or?
Wait, it's F. So wait. F.
it's the same.
Same, yeah, that is the two units.
Guys, I just get the brush here. Thanks, Robert.
Yeah.
Okay. We will need to do, we're gonna go over page 100 together. I'll go over with you on the iPad, Java. It's a little more harder. So start on that. Check these first. Make sure this should all be review, basic review. But page 100 is a little more difficult. It's combining kinematics with forces. So you can start on that. I'm gonna walk you through it in a minute. I'll start on number 7, but check these first. Make sure you know what you're doing here first.
Gravity is.
Force of gravity is weight, yeah. Fg means force of gravity. It's the same thing as weight. Yep.
Oh, Jesus.
All the equations. Look at that. Okay, we'll run in all of this. There's a back page too.
Carlos Linnaeus. Carlos Linnaeus. Census. Holocaust. Confucius. Abacus.
Textbook.
Gus.
Oh, yeah, so you saw that shit.
Bus. Bus.
Yeah.
I subscribe to it, and it's like,
Okay, so I'll start going through page 100 with you. You can follow along, work at your own pace. That's weird. They copied it. Whatever. Okay, so 100, 100 number 7. Just read it carefully to yourself here. Okay, so I'm after the net force. I need to find the acceleration. Whatever the direction of the acceleration is the direction of the net force. I can tell you just by looking at it, you're accelerating to the south. Acceleration is southerly. The net force is southerly. Okay, now let's calculate the acceleration. I need that for the force. So make a list of what you have. You start from rest. You accelerate to a velocity of 25 in 10 seconds. I need the acceleration. I'm just going to insert positives before I go on here. Let me finish, please. Before I go on here, it is moving 25 meters per second south, so you can put a negative there if you want. Okay, or you can keep it simple. You can just realize that since it's moving in a southerly direction, your final answer will be south. You can still use positives as you want. Just remember to insert the direction in the end. I'm solving for acceleration. So VF is 25. Yes, you can put negative. That'll give you a southerly direction as expected. I already know that though. I anticipated that. Whatever you prefer. So that works out to be 2.5 meters per second squared. You're moving in the southerly direction. This is going to be south. Or you can put negative 2.5. Now was the question. You got a question? I knew that. I was testing you again. You were right to ask me that. You guys are so, that's good. That's good. You passed my second test. You're just so aware and focused. I'm impressed. Don't laugh at Mr. Kenyon. Mr. Kenyon is always on the ball, testing you. Remember that. That's it. Sorry, guys. My apologies. There's your work. It's coming. Give it time. Well, I'm going to keep 3 for now, and then I'm going to use it to calculate the force, which will be 2, then round to 2. If it's a 2-step problem, you can, in this case, find an answer in 3 sig figs. F net is equal to MA. Take the mass, multiply by 2.5 or negative 2.5. As long as you remember to put it in the end, that's fine. That works out to be 2.3 times 10 to the 3 newtons south. Or you can say, or negative. Either one. Eight. Read over 8. To yourself, read it over. Same basic premise. You need to find the acceleration to find the net force. You're not given a direct, actually you are, north. So you're traveling north. That's going to be north. That will be north. Okay, find the acceleration. So I would make a list. Accelerates from rest. Travels 132 meters. I know that's north. I'll leave the direction out. I'll just use magnitude here. And I want to find acceleration. So this is your list. Find the equation that contains all 4, which is this one. Okay, where this first term on the right is 0. The I is 0. 0 times anything is 0. I've dropped the vector notation. I've just used absolute value. I know my final direction is north. Hey, go back to here. 0.83. That works out to be 1.98 or 2. Don, you put your direction in at the end. Okay, I would, just for clarity's sake, if you want to use positives and negatives, make sure you put a positive in front then. You can put a positive in front, or you can put north at the end like I did. That's the final answer. Can you, okay. Are you asking to solve for the final answer? Yep. It's 2,000 newtons. 1.98 times 10 to the 3, or rounds up to 2 times 10 to the 3. Number 9. Read it through. I'll go through a little faster. It's going to be east. It's going to be east. Same direction. VI is 5. VF is 12. The distance is 94. What's the acceleration? We want the acceleration to find the force. Use this equation here. Solve for, know how to rearrange for the acceleration or the distance. Those are common questions. And your acceleration is 0.633. And yes, it's east. You'd end up with a positive value, so it's east. So your force is east. Hmm. 7.6, 760. East or positive. Number 10, I'm going through it a little fast here. Take a quick look. It's being recorded. 10, read it through. I'm going to solve for the mass by dividing the force by the acceleration. I've got the force. I need the acceleration. Make a list. Remember the conversion factor. Divide by 3.6. To find meters per second. Solve for the acceleration. There's a list. Find the equation that contains all four. .67. Okay, I'm just interested in magnitude. It's going to be north, just so you know, but same direction as the force. All I need is the magnitude. F net over acceleration equal to mass. F net is 2,500. Divided by 2.67 is about 940 kilograms. It's a scalar, no direction. 11A. Read that. Same direction as the force, east. How far did the object travel? How far is just the distance? Starts from rest, undergoes an acceleration, reaches a final velocity east as well. And we want to find how far your distance is going to be east, because everything else is east. Question mark. Circle it. Find the equation that contains all four. Solve for the D. You need to know how to do this routinely. And your D works out to be 6.1 meters. Same direction as the others, east. Same direction as the other. Everything is east. Everything else is east, so displacement is east. If they ask you if the question is how far, you just have to give an absolute value. What is the time? Go back to this list. Direction is going to hurt. Well, you can include it if you want, but. And then instead of D, insert T. That's your list. Okay. I got something for you. Give me a second here. Nothing on ink lines in this book. Okay. I have to do that myself. So your homework is in your textbook. You can take pictures of it if you want or take it home. Read pages 100 to 109. I will make some notes. If you want to make notes, you can. I'm going to make some notes on it as we go through the following questions. And then when I give you the handout that's coming next, do page 108. All right, give me a second here. Yeah, 108.
I'm not sure.
1 to 3. And then page 114, 1 to 6. And then, okay. So you've got the book. You can take it home. You can leave it here if you so choose. Take pictures of those pages. And then do the pages that I just outlined, what I'm going to give you next, coming around. So page 108 and 114 are in the following handout. Yeah, give me a minute. Well, So again, page 108, 114 are in this handout as your page. Of your drive handout. Page 100, what question was that again? Number 8? 10? $940 kilograms. And the other question? Utilities, descriptions, yeah, you have to square it. Yeah, you have to square that. You square it after you go, square it after. Yeah. So that would be, here's your one touch stuff. It would be just the square root of that, divided by 12, not the square root of the whole thing. Make sense?